Good morning. We're going to do it like this, and then a little bit like this, and a little bit like that. Oh, not quite. Hold on. Connect this off the camera. Restart this. Sorry, give me just 1 second. Dot camera is okay. Dot cam is acting up just a little bit. There we go. And there we go. All right. Let's do that. Okay. So I have 1 or 2 things that I wanted to play around with you guys today, but I would be happy to work on any particular things that you guys wanted to also, as being a kind of like our lab day. So the example I was hoping to play with a little bit is something called a cycloid. I did it with my pre-calc and trig kids the other day, and it's such a fun construction that I thought you guys would probably enjoy it too. But before I get into that sort of thing, is there anything that you guys feel like looking at? Anything from those Taylor series problems or from the parametric curves homework that's been bothering you so far? Maybe I should give just another moment or two. Any larger questions or complaints or uncertainties? Anybody worrying about exam stuff, grade stuff, assignments, anything like that?
On uh on Canvas, I'm pretty sure it says that there's an exam tomorrow, April 17th. So I was just making sure that's not the case.
It is not the case that there is an exam tomorrow. It is the case that on the 24th, I will give you the exam 3 as a take-home. So when I originally set this up, I wasn't planning for exam 3 to be a take-home. I was planning for exam 3 to be an in-class exam that we would take the second to last week so I could get it back to you and we could use it as a review tool for the final in the last week. So I will change the date in Canvas. I appreciate you letting me know. But yeah, no, it is not the case that you have an exam tomorrow. The last midterm exam for this class, the last regular term exam for this class is going to be exam 3, which will cover the Taylor series, polar and parametric curves, and it will be a take-home that I give you on the last regular day of class, which will be due on the day of the final. That's good though, I'm glad you asked that. What else are we wondering? Is there anything else like that? I don't want you guys to be losing sleep over these things. Otherwise, feeling pretty good? I swear this camera, man. Well, that's a little better. So lately we've been talking about parametric curves. And one of the more fun examples, I guess we can go through a couple other kind of silly examples before I do the cycloid, because the cycloid construction is a little bit tough. So we've seen that the set of parametric equations x of t equals cos t and y of t equals sine t will give us either the whole unit circle or a portion of the unit circle, depending on the range of t, right? Depending on the time domain I specify. I don't know why this camera's having such a hard time focusing this morning. Can you guys read that okay?
Yeah.
It's a portion of the unit circle. So some of the fun things that you can do with parametric curves, I don't know if you guys ever, when you were in high school experimented with getting your TI-83 to draw Batman or anything silly like that, can be with modifying these things. Starting with the circle example is a great way to start like exploring what parametric curves can do. So if you haven't done this before, I think it might be fun to go through it. You can ask yourself, how would I change this to make an ellipse? How would I change this to make some kind of crazy spiral? What sort of different shapes can I make, starting with this circular thing? It'll help give you a feel for what the parametric curves or parametric equations do to the curve. So kind of one of the first easy examples to play with like this is sketching something like this. So one of your homework problems is to show that if you multiply both of these equations by some constant, that just increases the radius of the circle, right? So like 2 cos t, if x of t was 2 cos t and y of t was 2 sine t, instead of giving me the unit circle, the circle of radius 1 centered at the origin, it would give me the circle of radius 2 centered at the origin. But what happens if I just multiply x by 2 and I don't multiply y by 2? The cos t comma sine t thing is still trying to get me to do a circular type motion. But now the x's are able to run from 2 to -2. The y's are still only able to run from between 1 and -1. So if I still have that same circular behavior, but I stretch things out in the x direction, we have reason to suspect that this would be an ellipse, and it is. So we want to sketch this guy, which intuitively ought to be some kind of stretched out circle. Right, because regular old cos t comma sine t gives me the unit circle. Here, I'm multiplying all the x coordinates by 2 and leaving all the y coordinates alone. So it's like picking up the paper of the unit circle and just pulling it out like this. And there's a lot of shapes that are stretched out circle things. But the first one that comes to mind for most people is an ellipse, and this does happen to actually generate that conic section, that exact thing. We can make a table if we're uncertain. That's always a fine place to start. And I'll plug in some kind of natural choices for t. And we'll see what we get. When t is equal to 0, that's going to be my initial point. X of t is 2 times the cos of 0 is 2 times 1 is 2, and y of t is 2 times the sine of 0, sorry, is 1 times the sine of 0 is 0. When t is pi over 2, that's 2 times the cos of pi over 2, that's 0, and the sine of pi over 2 is 1. When t is equal to pi, I get 2 times the cos of pi, that's -2, and sine of pi is 0. Oops, sorry, that's a 0. When t is 3 pi over 2, the cos of 3 pi over 2 is 0 again, the sine of 3 pi over 2 is -1. And when t is 2 pi, cos of 2 pi is 1 and sine of 2 pi is 0. So the curve shape that I get here, we can anticipate what it is, based on the discussion above. It's the same equations as for the unit circle, just with all the x values multiplied by 2, so I expect a stretched out unit circle. And that's what you get. So if this is 1 and this is 2, there's my initial point. And then as t starts to increase, you think about what these two functions do as a function of time. Sine t is an increasing function of t. So as t starts to increase from 0 up, Sine t is getting bigger, so the y values are getting bigger, so we're starting by coming out like this. And the x values, cos t, starts off decreasing, so we're coming in something like this. So I know that my orientation is going to start off looking like that. And then the next point I have from my table, when t is pi over 2, is 0, 1. So let me go ahead and mark these off. 1, negative 1, negative 2, 1. So the next point I know for sure, this was when t equals 0. This guy appears when t is pi over 2. And so what is this curve doing? It's doing something like this. Y values are increasing from 0 to pi over 2 because sine t is an increasing function as t runs from 0 to pi over 2. The x values are coming in because cos t is a decreasing function from 0 to pi over 2. And we know that this point right here, 0, 1, that's the next point that's on my graph because that's the next point that's on my table. And then next, after that, we're going to hit negative 2, 0. This is when t is equal to pi. Oh, and we should come in, yeah, like that. And then I have 3 pi over 2. We're going through 0, negative 1. And then when t gets to 2 pi, we're back to 2, 0. And this shape does turn out to be an ellipse. So that set of parametric equations graphs as this curve. This is a conic section called an ellipse. And we can find the Cartesian equation for this too. I don't know if you guys had a good study of conics in your pre-calculus class. Some pre-calc classes do, some don't. Does anybody remember the standard form Cartesian equation for an ellipse? It's kind of like the one for a circle. It's more similar to the one for a hyperbola, if you remember that. Well, let's discover it. You remember when we eliminated the parameter in the parametric equations for the circle to get x squared plus y squared equals 1? How did we do that? What made that go? Feel free to look at your notes from, I think it was just yesterday, right? We started with the fact that sine squared plus cos squared equals 1, right? And then because cos is x and sine is y, saying cos squared plus sine squared equals 1 was the same as saying x squared plus y squared equals 1. And we're like, oh shit, that's it. That's the regular Cartesian equation for the unit circle. Well, here, it's not going to be the case that if you square this, and add them up, you're going to get 1, because 4 cos squared t plus sine squared t is not 1. But what will work, so let's eliminate the parameter. Find the Cartesian equation. I have x equals 2 cos t and y equals sine t. So if I divide this equation by 2, I'll get x over 2 equals cos t. And this guy stays y equals sine t. So now if I square these and add them up, right, so I divide both sides by 2 here to get this. And now if I square these and add them up, I will get 1, because that will be cos squared t plus sine squared t. And so I get x squared over 4 plus y squared equals 1. And the standard equation for an ellipse centered at 0, 0 is x squared over a squared plus y squared over b squared equals 1. So we can recognize this as x squared over 2 squared plus y squared over 1 squared equals 1. That's the equation of an ellipse centered at 0, 0 with semi-major axis along the x-axis and semi-minor axis along the y-axis. If you haven't studied conics and you don't recognize that equation, that's okay. It's not the end of the world. But you see how it's very similar to the equation for a circle, right? Circle is x squared plus y squared equals r squared when you center it at the origin. This guy doesn't have a radius, right? He doesn't have a constant radius, so his equation is going to have to look a little bit different. And so instead of having an r squared on the right-hand side over here, each of these variables is divided by a different constant, and that tells you what direction the ellipse is stretched out in. So this really is an ellipse, because these parametric equations, when you eliminate the parameter, give you this equation, which is definitely the regular Cartesian equation for an ellipse centered at the origin. Cool stuff, right? So starting to fiddle around with known sets of parametric equations to create new ones is a great way to build your intuition as to how these things work. In a sense, it's very nice because the x's and y's are divorced from one another, right? They don't mess with one another directly, so you can fiddle with the x's independent of fiddling with the y's. And that's what allowed me to create this ellipse from the unit circle. I was able to stretch out the x coordinates without doing anything to the y's, because the system of equations, or the set of equations that gives me that graph, has both of them as functions of time, rather one as a function of the other. And that's super convenient for little experiments like these. Some other fun things to do with the unit circle. We said if I multiplied each of these by a constant, then that would just increase the radius of the circle. If I multiply each of them by different constants, then that will kind of increase the radius in one direction different than in the other direction, and so you'll get an ellipse. But if you start multiplying them by non-constant things, you can get fun shit too. Other good questions to ask: what would happen if I changed t to negative t here? So I'm just starting to ask, what happens if I start multiplying in all of the obvious places by different constants? I can multiply on the outside by positive constants. If they differ from each other, I'll get an ellipse because I'll stretch things out. If I multiplied by the same constant, I'll increase the radius. What if I multiplied on the inside by -1? So if you think of this as an ant kind of walking around this path, right now as t increases, he's walking in this direction. And if I multiplied by a -1 on the inside of both of those functions, what do you think that would do to this curve? What do you think that would do to this path? What would change on this picture?
Would it flip to the opposite direction?
Yeah, the orientation would change. My little guy is still going to walk around that same path, but now he's going to walk around it in the other direction. Desmos can also be a good tool for playing with this stuff, and I wanted to show you a little bit of the fun that you can have in Desmos with these things. Don't spoil that yet. I'm going to be brave and just share my whole screen. There you go. So if you enter these as ordered pairs, right, like x comma y, you put the x equation in and then you put the y equation in, x equation in the first coordinate, y equation in the second coordinate, then Desmos will graph parametric curves for you, and it'll graph them very nicely. Here's t running from 0 to pi, this is pi over 2. This is our ellipse, the one we just graphed. And then 0 to pi, and then 0 to 3 pi over 2, and then 0 to 2 pi. So you can kind of get a feel for it. by increasing t manually. Now, if I change t to negative t, we don't see what's going on right away, but like you said, I think that was maybe Austin, I wasn't sure who said that. If you change that t to a negative t, yeah, you just end up walking around this thing backwards. So there's to pi, there's to 3 pi over 2, and all the way out to 2 pi. All right, I bet we could put a slider in here. I'm just not sure how to do it. Yes, it's not super clear. I don't want to burn too much time on this. But that's okay. So what's this here? Okay. So yeah, changing t to negative t reverses the orientation. One of the other fun things that we can do is instead of multiplying by a constant on each of these to increase the radius or to increase the radius in one direction, stretching it out, is to start multiplying by variable quantity stuff. So what happens if I multiply both of these by t? So I'd get the equations x of t equals t cos t, and y of t equals t sine t. Well, if that was a 2 or a 3 or a 4 instead of a t in front of both of these, then I would get a circle of radius 2 or 3 or 4. And you can still sort of think of it as a radius, it's just that it's not a constant anymore. So imagine you are walking around a circle, but as you walk around, your radius increases. What kind of path are you going to take? Can you picture it? Think about it for a minute. Imagine you're just walking around in a circle, but every time you take a step, somebody comes in and pushes you radially outward. So for every step forward you take, you get pushed out like a foot.
Like a spiral.
Spiral?
Yeah, it's going to be a spiral. Now, when t is equal to 0, both of these are 0 because of the t multiplying them out front. Doesn't matter that cos of 0 is 1, this is going to be 0 times 1. So your initial point is going to be right here at the origin. But then you start trying to do this circular thing, and you're taking these little steps outwards each time. So you're going to poke out like this. And when t is pi over 2, you're going to be at here. Well, this would be pi over 2, comma, or pi over 2 times 0. So this would be 0. And this would be pi over 2 times 1. So by the time you've rotated up to here, you've walked out pi over 2. And then as you come out here, you'll have walked out pi. You'll have walked out 3 pi over 2. You'll have walked out 2 pi, and so on. Now, my pictures are never quite perfect, but it's going to be like this. Yeah, it's going to be a spiral. Because you're walking around in a circle, but you're also getting pushed out away from the origin as you walk. So if I wanted to graph this 0 less than or equal to t less than or equal to 4 pi, that's 2 full walks around, so I'm going to continue coming out. Something like this. All right, and this would be my terminal point. And this in here would be my initial point. And with everything that we've learned in the last few days, we could come in here and find all of these places where the tangent line is horizontal, like here and here and here and here. We could detect those with calculus now by setting dy dx equal to 0. We could also find the places where these tangent lines are vertical, like here and here and here and here and here. And just experimenting with this shit's a lot of fun, so I encourage you to do it. Play with this stuff in Desmos. Here, I'll graph this one for you. Oh, yeah, there it is. And if we let t run all the way out to 4 pi, you'll see this is actually a special kind of spiral called an Archimedean spiral, because the radius is increasing at a constant rate. So you get this kind of neat, consistent shape. If I multiply by any other monotone increasing function, like here I just multiplied by t, but if I multiplied by e to the t, and e to the t, then the spiral is going to radiate out much, much faster. And this spiral is actually very closely related to a famous one, that Fibonacci spiral. This is actually called a logarithmic spiral, and it does a very, very good job of approximating that spiral that you see when people act silly, like Dan Brown thinks he knows something about mathematics, and wants to talk about, call it sacred geometry or something silly like that. But there are neat ratios built into this sort of thing, and it's a very good approximation of that Fibonacci spiral just by slapping an e to the t onto each bit of the equations for the unit circle. We already looked at t times these, so if I increase the radius as the natural log of t, that actually gets really interesting too. I can't start at 0 anymore, because the natural log of 0 is undefined. But if I do like this, no s, there it is. The natural log starts off growing at a pretty reasonable speed, but as you get out there, cos t ln sin t, yeah, as you get out there, he really starts to grow very, very slowly. So let's do something like, this. So things get very, very dense, because at first your radius is getting pushed out quite a lot each time you go around. Each step forwards you take, you get pushed out a decent amount, because the natural log function starts off growing rather quickly, right? If you look at the tangent line, the rate of change for the natural log when t is equal to 1 is 1. So it starts off looking a lot like that, the spiral that we just drew, right? It starts off looking a lot like this spiral. But as t gets larger and larger, the natural log still grows, so you're still getting pushed out, but it grows less and less and less and less, right? The derivative of ln t is 1 over t. So the size of the steps that you take out for every step you take forwards along this spiral gets less and less, and so things get very dense out here. So there's all sorts of fun things you can do playing around with this stuff, and I really want to encourage you to play around with it and start to get a feel for it. And I think taking the equations for the unit circle and then messing with them is a good way to do that, rather than starting from scratch and going, well, what the hell do I even do? Like, having something that you can treat as a prototype that you can then fuck with is a good way to try and build that intuition. There's one other really important example of a parametric curve, and it's I'm gonna cook up the curve for you, and then we're going to do some calculus with it. We're going to get a little bit of practice doing the calculus operations on them. So I'm going to want to find the area underneath this thing, or the area enclosed by it. And we haven't talked about areas in the parametric setting, but it's actually kind of boring and kind of easy. But then I also want to find the length and want to find the horizontal tangents and the vertical tangents. The thing I'm thinking of is called a cycloid. You may have seen as a bicycle rides past you on the street, especially at night, especially if you're in a car and you've got the headlights shining, you can see the reflectors on their wheel making this really neat pattern. because as the wheel goes around, the reflector goes around, but also the bike and the wheel are moving forwards. So it's not just sitting there and spinning in a circle. If you know what I'm talking about, then this should look familiar. Right, this is the pattern. There's the rotating wheel, and imagine this is like the light or the reflector on the wheel. As the wheel rotates, the reflector goes around, but because the wheel is also moving forward, it traces this kind of interesting looking path. The first time I saw one of these, I was like, oh shit, that's half of an ellipse. And I was wrong. It's not an ellipse. It looks kind of like half of a stretched out circle-y thing. And so I don't think it's an unreasonable guess or hope that it is an ellipse, but it's not. It just doesn't have the right geometric features to be an ellipse. It's something else, and that something else is called a cycloid. So what I would like to do is I'm gonna draw this picture here with a rotating wheel, and we're gonna find the parametric equations that give this light blue curve here. And it's not gonna be that tough, but there is a fair amount of geometry involved. So it's an exercise that I enjoyed going through with my trig pre-calc students the other day, and I thought that since you guys are also talking about parametric curves, it would be a good thing for us to do too. So let's find the parametric equations for the cycloid generated by rolling a wheel of radius r, say. So I'm going to imagine I have a wheel of radius little r, and somebody, put a little light or a sticker at one point on the edge of the wheel, and I'm going to track the path that that sticker makes as the wheel rolls forwards. So here's what's up. I'm going to imagine that some point P along that wheel, that's the point I'm going to tag and follow, the point that's going to make this path, started right here at the origin with the wheel above it. But I'm going to draw the picture just a little bit later. So if my point P started here, imagine rolling this back, that point P here, and then rolling it forwards. Maybe that point is like here now, somewhere right around here. Okay, so here's the center of my wheel. I'm going to draw the vertical down from the center, and I'm going to draw the radial line out there. I'll call the origin O. I'm going to call the point that I track P. I'll call the center of the wheel C. And I'm going to call this point of tangency down here T. And then there's one more thing that I need. I'm going to create a little right triangle in here. I'm going to call this angle theta. Okay. So theta is the little angle in here. And it's the angle through which the wheel has rotated, right? To get from here to here, to get from P being down here to P being up here, this wheel had to have rotated and rolled along the ground a little bit. Now remember that the radius of the wheel is r. So this distance from the center to a point along the edge of the wheel is r. I'm sorry, my art is bad and I feel bad. It's a little more circular now. So my goal is to find P, the coordinates of P, the x and y coordinates of P, as a function of some other parameter. And this time the parameter is going to be theta rather than time. You can think of theta as also being t. I mean, if I wanted to label it as t instead of theta, I could have done that, but I'm calling it theta because we're going to do some trig. So P is x comma y, and I want to find x and y as functions of theta. So my parameter here, instead of t for time, is going to be theta for the angle the wheel has rotated. A few things I need. I need this distance, because that's the distance the wheel has rolled. So the length OT, I don't know if you can see this, the length from the origin to the point of tangency down there, it's equal to the arc, the length of the arc along the wheel subtended by theta. So does anybody know what the arc of a sector of a circle is? The arc length for a sector? If I give you a circle like this and I say, okay, well, this is theta, how long is this arc? Does anybody know that?
Isn't it S equals R theta, or?
Yeah, it's r times theta, right? The easy way to remember is 2 pi r is the circumference. And so theta times r is the arc length of a sector. Right? It has to be a linear function of theta, and it has to be equal to 2 pi r when theta is 2 pi, and it has to be equal to 0 when theta is 0. That means the only thing it could possibly be is theta times r. Right? You might want to think a little bit about why it has to be a linear function of theta. That's maybe not super obvious, but I contend that it's fairly obvious. And then being 0 when theta is 0 and being 2 pi r when theta is 2 pi, those should be fairly obvious. So the length OT here, my reel here is of radius r, and I've rotated through theta, so this is r theta. Now remember what I'm after. I'm after the x and y coordinates of this point P. I'm going to come in here and label one more point. I'm going to call that point Q, where this horizontal line hits this vertical line. Because now I've got a little right triangle in there. PQC is a right triangle, and I'll be able to use some trigonometry. So the distance x that I want is this, and the distance y that I want is this. All right, those are the x and y coordinates of the point P. X, this distance, has to be the distance from O to T minus this distance, which is the horizontal distance from P to Q, right? So x is equal to OT, that's this distance, minus this distance. And this distance is the same as this distance. So the distance I want, x, is equal to OT minus PQ. OT we'd found just a second ago comes from this length of a sector of a circle business. So that's r theta minus, and then to find PQ we need some trig. Notice that the side length PQ is opposite this angle theta, right? If this is theta, then PQ is the opposite side in this triangle. So I look at the sine of theta. The sine of theta would be PQ over r. You could include this down here in this sort of scratch workspace if you wanted. Which means that the length PQ is r sine theta. So OT minus PQ, OT is r theta, so I'm going to subtract PQ from that, that's r sine theta. So this is r theta minus r sine theta. And that's x as a function of theta done. So to finish things up, I need to come back in here and do the same game to find my y's. Y, this distance, is equal to this distance minus this distance. Yeah? Maybe if I have two things to point that aren't fat like my fingers. This distance is the same as this distance, which is this distance minus this distance. Everybody see that? This is y, and it's the same as this. This is this minus this. So y is the same as CT minus CQ. From the center to the point of tangency at the bottom, minus from the center to Q. That will give me this little horizontal distance. It's the same as QT, right? Really what I'm after here is QT. And QT is CT minus CQ. CT is the radius of the circle. So that's just R. And CQ is the adjacent side length in that little triangle. So if I look at the cos of theta, I know that the cosine of theta is the one that involves the adjacent side length. That's the adjacent over the hypotenuse, so that's CQ over R, which means that CQ has to be R cos theta. So this distance CQ that I'm subtracting here is R cos theta. And that's all the work done here. So my parametric equations are x of theta equals R times, I'll factor out the R times theta minus sine theta. And y of theta, factor out the R here, and you get 1 minus cos theta. So that's how we derive the parametric equations for the cycloid. And if we come back over to Desmos, I think I have one of these up here. Yeah. So I imagine my circle. Start off like this. And as my circle rotates, that path is going to be created, right? So here's the point that I'm tracking. It's this point down here. And as this circle rotates, that point is going to move up and along, and then a little while later, it's going to be right here. And then a little while later, it's going to be down here. And as you let t increase, out to where, let's say 4 pi, you get this neat little cycloid path. So my next question for you would be, can you find the length of one loop of the cycloid? Can you find the points where you have horizontal and vertical tangent lines? And maybe even can you find the area underneath one of these guys? So all of those sort of calculus questions we can ask in this setting now. I am going to swap theta for t because I'm just a little bit more comfortable working with the parameter t. So let's find horizontal and vertical tangents. Find the location of horizontal and vertical tangent lines to x of t equals r times t minus sine t, and y of t equals r times 1 minus cos t. And I'll let t run from 0 to 2 pi. So I don't end up, we know there's, this continues like this forever and ever if you let t run off to infinity. So I'm just going to look at one cycle. How do I find horizontal or vertical tangent lines for parametric curves? What is it that I need in order to talk about those things? Well, horizontal and vertical tangent lines, I'm talking about tangent lines of a certain slope, right? Horizontal tangent lines, those will be tangent lines whose slope is 0. Vertical tangent lines will be tangent lines whose slope is infinite. So I need to get the calculus object that gives me the slope of the tangent line. What is that?
The derivative?
Which derivative? You're right, yes. What derivative, though? dx dt, dy dt, dr d theta? Don't overthink it, you know this.
Oh, is it dy dx?
Yeah, I need dy dx. dy dx is the differential object that gives me the slope of the tangent line. And normally I have y given to me as a function of x, so I just differentiate that and I get dy dx. But here, I don't have y given as a function of x. I have both x and y given as a function of time. But last class, we talked about how to get dy dx out. You look at dy dt or y dot, and you divide that by dx dt or x dot. So here, y dot, the derivative of y taken with respect to time, what is that? I differentiate y of t with respect to t. What do I get? R is a constant, 1 is a constant. So maybe it's easier if you think about distributing this. This is r minus r cos theta, or r minus r cos t. If I differentiate that with respect to t, the r goes away, and negative r cos t differentiates to r sine t. Right, if I differentiate this equation right here, I get r times the sine of t. And if I differentiate x with respect to time, this r is going to come along for the ride. This t will differentiate to 1, and this sine t will differentiate to cos t. So I'll get r times 1 minus cos t. And that's kind of neat. In fact, you can describe the cycloid in terms of a set of differential equations, x dot equals y. That's kind of cool. But what I want to know is, where do I have horizontal and vertical tangent lines? So what is it I need to do with dy dx now that I have it? Go ahead and look at notes from yesterday. We just talked about this yesterday. Horizontal tangent lines are places where dy dx is equal to what? When dy dx is 0, right? dy dx is the slope of the tangent line. So if I want to know when is the tangent line horizontal, i.e. when does the tangent line have slope 0, I set dy dx equal to 0. So that's going to be when sine t over r times 1 minus cos t is equal to 0. When does this happen? Well, I can cancel the r's. fraction is 0 when its numerator is 0, right? If the top is 0 and the bottom's not 0, then a fraction is equal to 0. So this will be true when sine t is equal to 0. And we know when sine t is equal to 0. Sine t here, we graph this out to 4 pi. So let's go out to 4 pi. We'll take all the solutions from 0 to 4 pi. Sine t is equal to 0 on that interval when t is equal to 0. When else? Pi, 2 pi, 3 pi, and 4 pi, right? Sine t is equal to 0 when t is a multiple of pi. So I have reason to suspect that I'll have horizontal tangent lines when t is equal to any of these. But the thing we need to watch out for is that we're not also making the bottom 0, right? We don't just need sine t equal to 0, we need the bottom to be non-zero. So when is the bottom equal to 0? When is cos t equal to 0, equal to 1? So we have problems when cos t is equal to 1. That's when t equals 0, 2 pi, and 4 pi. So I definitely have horizontal tangents, HTLs, when t is in the first list but not in the second list. So that's at pi and 3 pi. And I'm not sure what happens when t is equal to 0, 2 pi, or 4 pi. Right, so a fraction is 0 if the top is 0 and the bottom is not. I can say that for sure. The top here is 0 at any integer multiple of pi. And at the odd integer multiples of pi, the bottom is not 0. So I know for sure at the odd integer multiples of pi, I have horizontal tangent lines. At the even integer multiples of pi, the top and bottom are both 0. And so it's not immediately clear what to do. When t equals 0, 2 pi, 4 pi, etc., dy dx looks like 0 over 0. So how do we handle that shit? What's the calculus tool for dealing with ratios that look like 0 over 0? Anybody?
L'Hopital's?
Yeah, we can L'Hopital rule this. We can look at it with a limit instead and L'Hopital it. So let's look at the limit as t goes to, how about 0 of dy dx. So we get 0 over 0, so we're going to use L'Hopital. The limit as t goes to 0 of dy dx is the limit as t goes to 0 of r sine t over r times 1 minus cos t, which is just sine t over 1 minus cos t. And if we're feeling like absolute calculus thugs, we could write both of those as power series and try to cook up the limit that way. I don't think we're feeling quite that calculus thuggish. So instead we'll use L'Hopital's rule, because the top here is definitely 0, and 1 minus cos 0, oh yeah, that's also 0. So we're going to L'Hopital it. Remember, you want to pick a notation to let your reader know you're using L'Hopital's rule. This is the one I like. So this will be the same as the limit as t goes to 0. Derivative of sine t is cos t. And the derivative of 1 minus cos t, well, 1 differentiates to 0. What does negative cos t differentiate to? He differentiates to sine t, right? And now as t goes to 0, what happens? Cos of 0 is 1. Sine of 0, though, is 0. So this looks like infinity. So as t approaches 0, dy dx approaches infinity. In other words, you found a vertical tangent line. When t is equal to 0. And we've already looked at the graph of this thing. We know that. We know that this thing starts off with a vertical tangent line, right? Look at this curve. Right over here. Oh, damn it. Right over here. The tangent line right here at 0 is definitely vertical. The first horizontal tangent line we found corresponds to this guy. What t value do you think is associated with this point right here, where we have our next vertical tangent line? So t equals 0, I had a vertical tangent line. I know that I had a horizontal tangent line when t is equal to pi. That's that first horizontal tangent line we looked at on the graph there. I'm going to draw in a cycloid here. God, that's shitty. A wobbly pen. So this point right down here, this is the t equals 0 point, where I have a vertical tangent. This point right here, this is the t equals pi point, where I have my first horizontal tangent. This next vertical tangent, if you do the same limit, but you send t to 2 pi instead, what's going to happen? Well, sine t is periodic with period 2 pi, so it does the same thing at 2 pi that it does at 0. Cos t is periodic with period 2 pi, so it does the same thing at 2 pi that it does at 0. If you did this limit with t going to 2 pi instead of t going to 0, everything would be the same. You would get infinity again. So that's our next vertical tangent. Sorry, I realize you can't see that. So this t equals 0 vertical tangent is the thing we just found by doing this L'Hopital's rule. This t equals pi horizontal tangent we identified way back here. This t equals 2 pi vertical tangent, I can say for sure is that t equals 2 pi is the time associated with this point, because if you swap this 0 for a 2 pi, this limit is going to go exactly the same, because sine does the same thing at 2 pi it does at 0. Cos does the same thing at 2 pi it does at 0. You would run L'Hopital's rule once, you would get this, and then cos of 2 pi over sine of 2 pi is 1 over 0 again. This guy right here, my next horizontal tangent, this is coming from t equals 3 pi. And then this vertical tangent here would be coming from t equals 4 pi. Does everybody see why those times correspond to those tangents? It's not terribly hard work that we did here. Right? We calculated dy dx. I set the top to 0. And I got this list of numbers. 0, pi, 2 pi, 3 pi, 4 pi. And it turned out that at half of those, the bottom was 0 also. I know that a fraction whose top is 0 but whose bottom isn't 0 is definitely equal to 0. But a fraction whose top and bottom are both 0, that's harder to deal with. That's why I use L'Hopital's rule. L'Hopital's rule told me that as t goes to 0, dy dx goes to infinity. So right here at t equals 0, oh, hey Nova. I know I have a, sorry, my cat just jumped up on my lap. This is the weird cat too. He never comes and says hi. Hey, say hi to the calculus class. Yeah, you're too shy to do this normally. Hello. So I know that right here at t equals 0, I've got a vertical tangent. And then you could just argue through periodicity, right? These are both periodic functions of time. So the period is 2 pi, so whatever it's doing at t equals 0, it'll be doing at t equals 2 pi also. Okay, whatever it's doing at pi, it'll be doing at 3 pi also. Why are you so affectionate this morning? Weirdo. Yeah, you're a weirdo. Yes, you are. So have I solved the problem? Have I found the location of the horizontal and vertical tangents for this curve as t runs from 0 to 4 pi? Oh, it's okay, you can lay down. Is the question clear? Very sweet. I'll answer it. We have not. No, we haven't finished the problem yet. Because we were asked for the location of the tangents, right? The location of the vertical and horizontal tangents, and I gave the times. So let's recap and then finish this up. So we have discovered that the cycloid x of t equals r times t minus sine t, y of t equals r times 1 minus cos t, where 0 is less than or equal to t is less than or equal to 4 pi, has horizontal tangent lines when t is equal to pi and 3 pi, and has vertical tangent lines, VTLs, when t is equal to 0, 2 pi, and 4 pi. So to finish things, I need to find the x and y coordinates. I was asked where are the vertical tangent lines, not when do I roll through them. So I need to tell my reader what the x and y coordinates associated with each of these points is. So when t is equal to pi, x of pi is r times pi minus the sine of pi. And the sine of pi is 0. So this is r times pi. And y of pi is r times 1 minus the cos of pi. Cos of pi is -1, so this is 2r. So that first point is at r pi, comma 2r. That's my first location of a horizontal tangent line. The other one is going to come from the t equals 3 pi. X of 3 pi is r times 3 pi minus the sine of 3 pi, which is sine of 3 pi is 0 again, so this is 3 pi r. And y, the y coordinate when t is equal to 3 pi, is r times 1 minus the cos of 3 pi. Cos of 3 pi, just like the cos of pi, is -1, so this is 2r. So this point is 3 pi r comma 2r. And those are my two vertical tangents, or sorry, my two horizontal tangents. This guy right here is r pi comma 2r. This guy right here is 3 pi r comma 2r. My vertical tangents, I've got three of them. When t is equal to 0, x of 0 is r times 0 minus sine 0 is 0. Y of 0 is also 0. It's r times 1 minus cos 0. So one of the points is 0 comma 0. That's this one. When t is equal to 2 pi, x of 2 pi is r times 2 pi minus the sine of 2 pi. That's 2 pi r. And y of 2 pi is r times 1 minus the cos of 2 pi. R times 1 minus 1 is 0. So this is the point 2 pi r comma 0. That's this point. And when t is equal to 4 pi, x of 4 pi, if I plug it in here, is 4 pi r minus the sine of 4 pi is just 4 pi r. And y of 4 pi is 0 again. It's r times 1 minus 1. So that's at these coordinates. So now I have finished. If I was asked to find the locations of any horizontal or vertical tangent lines, I would come back at the very end and say horizontal tangent lines are located at the points r pi comma 2r and 3 pi r comma 2r. Vertical tangent lines are located at 0, 0, 2 pi r 0, and 4 pi r 0. How do we feel about this? So for all these problems, it's the same procedure. You're going to cook up dy dx. You're going to find where dy dx is 0 or undefined. Places where dy dx is 0, those are going to be your horizontal tangent lines. But when you solve dy dx equals 0, you're going to get t values. You're not going to get points. You're going to get t values out. So in order to go back and find the point, you need to plug those t values into the original parametric equations. Similarly, when you find the t values for which dy dx is undefined, you're going to need to go back to the original equations, just like I was doing here, and plug those t values in to find the points. We can go back to the cycloid that we sketched here, where r was equal to 2, and you'll see that everything I said lines up. If r is equal to 2, 0, 0 is still 0, 0. The first horizontal tangent line at r pi comma 2r, let's see, would be like here. Well, if r is equal to 2, then this would be 4 pi comma, r pi, 2 pi comma 2r, r is 2, would be 4. Yep, there it is. So there's your first horizontal tangent. And then our next vertical tangent should be showing up at 2 pi r comma 0. R here is 2, so that's 4 pi comma 0. And this should be a VTL. And I'll zoom out and come over here. Yeah, sure enough, there it is, right? So you have some homework problems that will let you practice this skill, where you calculate dy dx as a function of t, find out where dy dx is 0, find out where dy dx is infinite, then take those t values and plug them back into the original equations to find the points. It's an important skill. We've talked a little bit about arc length, and I think I have time. Oh, it's close. All right. I would like to set up the integral for the arc length here, and then next time I will talk about areas. So maybe I'll extend the homework that's open a little bit into next week. The length of the arc along this cycloid. Let's just do one loop from t equals 0 to t equals 2 pi is, well, it's always s equals the integral of ds, and I'm going to integrate from 0 to 2 pi, and ds is the square root, so I'll say ds squared is x dot squared plus y dot squared times dt. So ds is the square root, I'll write it like that, the square root of x dot squared plus y dot squared dt. X dot and y dot, x dot I calculated earlier, that's r times 1 minus cos t. So this is r times 1 minus cos t all squared, plus y dot was just r sine t, so that's r sine t all squared under the square root times dt. So then s is the integral from 0 to 2 pi of this shit, which is, I'll write the square root in, r squared times 1 minus cos t all squared plus r squared times sine squared t. dt. So this is just sine squared. This is not a terribly tough integral. But it's not super easy either. We're going to have to square out the 1 minus cos squared. That's going to be 1 minus 2 cos t plus cos squared t. The r squared can factor and come out the square root as an r. And what's left under the square root is 1 minus 2 cos t plus cos squared t plus sine squared t times dt. And the good news is that cos squared t plus sine squared t adds up to 1. The r can come out of the integral, and I get integral 0 to 2 pi, square root of 1 plus 1 minus 2 cos t, that's 2 minus 2 cos t. Any idea how you would integrate that? Or how would you integrate just the square root of 1 minus cos t? Excuse me. So there's a trick you can play using half-angle identities here. I know we've run over time. I don't want to consume too much of your time. So I'm going to find in my notes where I calculated this earlier, and we can go through the details next time. Where's that? Yeah, right here. Okay. So this guy comes out to r times, I can factor out the square root of 2. Or no, actually, I can leave that in. Yeah. All right. R integral 0 to 2 pi. It's a trig identity. It's the same as 4 times the sine squared of t over 2. It's a sneaky trig identity thing. And so I end up just integrating 2r integral 0 to 2 pi sine of t over 2 which is a little micro u sub thing. This comes out to 8r. So the arc length calculation isn't terrible. It does come down to this kind of odd looking integral that maybe we haven't seen much like in the past. But the trick is to use a half angle identity, just in the direction you're not used to using it. You're used to using half angle or double angle identities to take sine squared into something that looks like 1 minus cos 2t. Well, here we're going to go from something that looks like 1 minus cos of t into sine squared of t over 2. So I only gave you a couple arc length problems on the homework this week. It's not terribly tough, and I invite you to play with them. Some of these arc length integrals can be brutally hard, and there's one problem that I would love to give you that requires power series expanding the integrand, but I'm trying to be a little bit gentle. I know life is a little bit rough right now, but I invite you to look into some of the arc length things that are out there. I posted a bunch of stuff to the modules in Canvas for you to play with. So please do take a look at that stuff. And if you get stuck on any of the homework problems, don't be shy about asking for help. Okay? All right, there is one area problem in there. And if you look in Canvas, I did post a resource for finding areas under parametric curves. You just integrate y times x dot dt. So if you're nervous about not having that formula, I'm out of paper, aren't I? Find the area under a parametric curve. You integrate y of t times dx. And dx is x dot of t times dt. And you would integrate from t equals a to t equals b. This only works if there is a notion of under, right? So this only works in the case where y is already expressible as a function of x. And that's what I meant when I said the area problem here isn't too interesting. But maybe next week, so I'll extend this homework through to Wednesday of next week, something like that. And we'll look at the area problem. We'll look at a few more arc length problems. So don't stress too hard, but please do get done what you can, especially anything asking about tangents or just sketching. It's important that you practice this stuff. This is cool stuff. And play around in Desmos. Generate new weird curves like those funny spirals and things that we were looking at today. I think you guys could get a lot of enjoyment out of just playing with that stuff because it can grant you a depth of intuition that you won't get unless you do play with them. Any questions about anything really? How the class is running, test stuff, grade stuff, math stuff? Okay, then that's where I'm going to stop it for today. Once this video finishes compiling, I will upload it to YouTube and post a link in the same announcement where you found the meeting link. All right, have a good rest of your morning, guys.